thank you very much for the invitation. It seems like a very interesting event that you guys are organizing. I'll try to show up tomorrow as well. Uh, so I was asked to give first an introductory lecture. Let's hope I achieve that in the first hour. And I was also asked to talk about something specific in the second hour, as far as I understand, which was some results about relationship of generalized complex and a specific type of Hermitian structures called SKT. So that it should be the content of the second hour. So let's go with the introduction to generalized complex structures. Let's see if I do this. Yes. No, that's a different file. Okay, here. So very quickly, generalized complex structures were introduced back in 2002 in Hitchens' paper on generalized Calabi-Yau manifolds, and were the topic of Gualtieri's thesis in 2003 that really worked out the initial theory in like a good amount of detail. It built on work of other people. So Weinstein and Severa had been already working on related topics since the 90s. Generalized complex structures are a generalization of complex and symplectic structures, and by being a common generalization, one definition that covers both cases, it automatically got attention of a lot of people, especially people doing string theory or mirror symmetry, that kind of thing, because seemed to be a unified framework for a number of things, including not only that these two things are examples, complex and symplectic, but also a number of concepts now have a unified approach. Within generalized complex geometry, like why is it not called something else? At the beginning, Hitching and Gualtieri had some conversations about what should we call this, and at first they thought maybe you should call it complectic or something, and yet they ended up choosing for a much lamer name, just generalized complex. But the idea was that they realized also very quickly that not only can do generalized complex, but it can do generalized Kähler, generalized Calabi-Yau, generalized hyperkähler, G2, spin 7, and you cannot do complectic for all of these. So somehow there was like a general framework that could be applied to a number of things that were already hanging around. And then the word generalized from this context just starts to mean geometry done on the sum of tangent plus cotangent bundle. So even though it's not a particularly inspired name, it's one that somehow has a precise meaning, and we can move on from there. It also relates to lower structures. So Kähler, Calabi-Yau, etc. means that you're putting more and more things. You're putting a metric and compatibility and so on. But also relates to things which are way more easy to find, like Poisson structures and foliations. And with that, it connects to the whole realm of Dirac structures, Lie algebroids, and Lie groupoids. That's where Severa and Weinstein were already working on since the 90s. And on the physics side, it connects with mathematics of string theory, especially type 2 string theory, type 2A to B. So that's kind of the realm that it belongs to. It started in 2002, had already all these things from the 90s on string theory and mathematics of string theory, and continue in that direction. The early questions we had for generalized complex manifolds included things like, are there generalized complex manifolds which are not complex or symplectic? And especially, we'd like to have somehow atomic ones, so to speak. So one obvious thing one could try to do is to take a product of something complex and something symplectic, that you could prove that, say, the complex is not symplectic, does not have a symplectic structure, and the symplectic does not have a complex structure, and hopefully the product would also not have either. That would be a little bit of in a way, a silly way to produce an example, because it's not very insightful. But at the same time, we lack tools to prove that higher dimensional spaces are not complex. So even if you try to just do products, it'd be very hard to prove that the product doesn't have, say, a complex structure. In an example, it's not a product, but just to get an idea, we still do not know if the 6-dimensional sphere is complex or not. So that's how much you're lacking in tools to prove that things are not complex. So even though it seems like taking products would be a straightforward way to get examples of manifolds without complex or symplectic structures, and therefore we should actually be looking into low-dimensional ones which are not products, there's also the part in which low-dimensional ones are the places where you actually have tools to check that things are indeed not complex or symplectic. So that was like one of the original questions. Can you find low-dimensional manifolds without complex or symplectic structures? But yes, with generalized complex. A similar one, going a bit the other way around, every generalized complex manifold is almost complex. And then one question is, can you find almost complex manifolds which do not admit generalized complex structures? This type of question kind of goes towards the realm of, does S6 admit a complex structure? We really lack tools to do that, to tackle this. Very early on, there was a question of special holonomy. So Marco was writing his thesis on generalized complex, and then Frederick Witt was writing more or less simultaneously a thesis on generalized G2 and spin 7 manifolds. For a long time, there has been a desire to understand what the generalized Riemannian curvature is. So there have been many proposals. It's something that we keep on struggling with until today. Relations with Poisson geometry, it relates with Poisson geometry in many ways. So try to explore those relations. One of them, for example, was the question of integration. In Poisson world, people like to integrate the Poisson manifold to obtain a symplectic groupoid. And then an early question was, what's the integration? What is there groupoid integrating a generalized complex manifold? What do they look like locally? So deformations and local forms, and do they relate to other types of string theory besides type 2B, to A to B? So those are a few of the early questions we had. They were all tackled in one way or another. So generalized complex manifolds without complex or symplectic structure, yes, they exist. And there was a sequence of papers producing more and more examples. They actually seem to be quite common. Almost complex manifolds without generalized complex structures, that's a tricky one. We still do not know whether that can happen or not. There has been recent progress. So Torres in 25 had a paper on indicating how one could try to deal with ruled surfaces and show that they are not stable generalized complex. Somehow the ideas of that paper seem to be interesting, that one can try to adapt them to more general cases. I've been working on that with my student Bas Vensik, but it's still inconclusive. And it does touch upon a number of things that end up like becoming symplectic geometry questions, like is there a symplectic manifold that violates the BMY line? The generalized special holonomy is something that Witt was already working on 2005, as I said. The definition of holonomy in generalized geometries is still not there. So somehow we have generalized spin 7, generalized G2, but that's kind of, we do these definitions by hand, not by saying there's a general definition of holonomy, and let's look at all the ones with special holonomy. The generalized Riemannian curvature is still ongoing, so it's neither like completely not known nor completely solved. That's why it's a bit in yellow. Gualtieri already introduced some notion of curvature that was further worked by other definitions as well, Coimbra and his collaborators, and Garcia Fernandez. So there is like currently a good amount of literature of different ways one could try to define Riemannian curvature and what the properties would be. So that's a very interesting one. I hope that Fernandez is going to talk about it in his presentation. Relations to Poisson geometry is something that came out many times, either because sometimes a Poisson structure determines a generalized complex structure, or sometimes because they are intimately related and allows it to deformations. So that appeared in the work of many people. The question of integration first appeared in the work of Kreinig in 2004, where he was kind of guessing what an integration could be, and Gualtieri 20 years later was proposed integrations and what the generalized scalar potential should look like. So there has been like a lot of progress on that direction, but it's a complicated theory. And there's a lot of questions about deformations and local forms. So a collection of things there. So deformation of generalized complex structures was studied by Gualtieri already in his thesis. Deformation of the generalized scalar structures, beautiful theorem by Goto in 2010. Bailey proved a local neighborhood theorem for generalized complex, saying that they are essentially holomorphic Poisson times symplectic. And with Bailey and my student Joey, we proved in 2019 a similar result for neighborhoods of special types of submanifolds, that and the whole neighborhood is actually given by holomorphic data. Other types of string theory, so originally it was type 2B, 2A to B, and then Garcia Fernandez, Rubio, and Tipler, as well as Baraglia and Hekmati, independently found that you can actually have a framework for heterotic strings, which is generalized complex. So in fact, you get the Strominger system from parallel spinor equations in the generalized complex rule. So that made like a new package for the whole thing that makes the theory, at least conceptually, more interesting. So what I want to do today, the first part, I'll just tell you something about generalized complex manifolds, try to especially focus on how one can produce those without complex or symplectic structures, what are the tools involved. And then a separate topic is just a framework for deformations of generalized complex manifolds. In the second part, I'll introduce generalized metrics, and then talk about Hodge theory on generalized Kahler manifolds and beyond, and deformations of those as well. So that's the plan. So right now, I didn't really tell you any mathematics, just like an overview of what happened. Is everybody okay? Can you guys hear me? If you have any question, just interrupt me, okay? So nice. First, geometry of T plus T star. So that's whenever we talk about geometry of T plus T star, that's what the word generalized means. For those who are not familiar with it, unfortunately, it's going to be a bit of a quick introduction on this part. But the idea is that first, you are given a manifold with what we call a background tree form. So you're just given that. Normally, we like to think in differential geometry that you're given a manifold and you put things on it. And in the generalized world, you think you have a manifold and a distinguished closed tree form. You can say, I don't like tree form. Where did that come from? So you can at first think of it as being zero, if you like. That's one of the allowed ones. But often, even if you start with them being zero, you may end up having to consider non-zero cohomology tree forms H. So that somehow is something that's always there hanging there in the background for you. There's always a manifold if this closed tree form. Once you have this closed tree form, you have this twisted differential. Just pick D and add this extra bit, which is H wedge. If instead of being a tree form, it was a one form, I would interpret that as a flat connection on the trivial line bundle. This, with the tree form, we interpret as being what comes next. It's a current algebroid is the name that goes with it. The idea is that T plus T star has two things on it. One of them is it has a pointwise pairing. So in this equation here, x and y are vectors, and psi and eta are one forms. You can just evaluate the forms on the vectors. So that's something you have because you have the sum of a bundle and its dual instead of just the bundle alone. So to get that whenever you have v plus v star type of thing. Here we pick the symmetric pairing. So we put a plus here. That one works well. A student of Rubio is working with what happens if you put a minus in there. That was something that people asked in the beginning, but in the beginning, maybe we didn't have enough understanding. So if you change that sign, you have to change other things in the theory. And if you don't, then everything goes like nothing works. So I think at the very beginning, somebody tried to change just that sign without changing the rest. And then we got nothing out of it. But changing the sign, you can actually go and develop a theory, but it's slightly different. And besides the pairing, you do have something else, which is this thing called the Courant-Dorfman bracket, which is written here. So that's where the tree form H comes in. So the bracket depends on that form. And the leading term here is just the Lie bracket of the vector fields X and Y. And then you get the Lie derivative of psi in the direction of eta, eta in the direction of X. And these extra terms here. So you see H appearing at the end. So that's the Courant-Dorfman bracket. The original bracket was written by appearing in Courant's thesis in 1990, and it was the skew symmetrization of this bracket. They just wrote, here's a bracket, and asked, like, is it possible that this bracket is the skew symmetrization of something more canonical? And then Dorfman came with the answer, and you know, in a very precise way, this bracket is more canonical than its skew symmetrization. This bracket does satisfy the Jacobi identity, but it fails to be skew symmetric. So it's not really a Lie bracket, Courant's bracket was schizometric but did not satisfy the Jacobi identity, so you have to give up on one of those two things to do T plus T star geometry. How does the bracket come about? So the idea is that if you have something, a vector in a one form, you can act on the forms on the manifold. The vector just contracts, so it decreases the degree by one, and the form wedges, increases the degree by one. So together they give you another form. So this highlights something that maybe you already were thinking or finding strange when I put the DH operator earlier, which is that this is not really compatible with just the composition of forms by degree. So if you like to think of forms as being like a K form, this is a bit weird because this one would be a K minus one form, and this would be a K plus one form. So automatically you mess up the degrees. The only thing that really remains is the even and odd decomposition. So if you have an odd form, you're active X plus Xi, you get an even form and vice versa. And the same thing happens for DH because D increases the degree by one and H by three. You should not really think of it as acting on K forms and getting K plus one forms. It really acts on odd forms and gives you even forms and vice versa. So the only thing that's left from the degree of forms is the even and odd gradients, the Z2 grading. One interesting property that this bracket, this action has, this action of T plus T star on the space of forms has, is that if you act twice, you end up with the natural pairing. So instead of being just an action like some other form, you just multiply the form rho by the norm of X plus Xi. So that means that this becomes an action of the Clifford algebra, and the space of forms become what you call the space of spinors for the Clifford algebra of T plus T star. And if you want to know what's the relation between the bracket and the DH, so how, like, why am I calling attention to these two guys at the same time? Essentially, you can try to do something like this. So here, X, Psi, Y, and eta, they're all acting on forms by contraction and wedge. DH acts on forms by just D plus H wedge, so the exterior derivative and wedge. And you can try to just take the graded commutator of these operators. Why would you do that? If there was no Psi and no eta, this would just give you the Lie bracket of X and Y. So this is Cartan's formula, one of them, for how the relationship between the Lie bracket and the exterior derivative. If you plug in a DH there, you get the Courant bracket, the Courant-Dorfman bracket from before. So that's what Dorfman came up with. So Courant just wrote a bracket, and Dorfman said, actually, you can realize this bracket in this way, maybe at first without the H, and then just get the untwisted Courant bracket. But with H, it works in the same way. So that's why this expression for the bracket is the one that makes more sense because it appears as this graded commutator. So that's something that also extends as the Schouten bracket is defined in a similar way for multi-vector fields. Graded commutator of D with action of multi-vector fields. So this kind of expression relating the exterior derivative with the bracket is an insightful one. And therefore, this bracket that we define here with the Courant-Dorfman is like a more insightful, a more canonical bracket than just the original Courant skew-symmetric bracket. One thing that we have extra on T plus T star compared with just the tangent space is that you can actually now act with two forms. Two forms have the following feature. They on the one hand, I can plug them into X plus Xi and just add an extra component here. So because B is a two form, it uses the vector to produce another one form. So it kind of shears, adds things in the T star direction. And so if I also make here a drawing, this is T and this is T star. What the two form does is that if you have a T vector, it does nothing. But if you have a T star, like once you have if you have something here, it will add up the B. So it kind of moves up. And if you're in T star, if you're just here, you do nothing. So that's kind of a transformation like that, if that makes any sense, like trying some sort of a graphical representation. It adds an extra T star component depending on the T component that you had. Oh, look at that, man. This sum is a mess. Okay, so that's from Jesus, I equals 0 to infinity. You can also act with with two forms on forms themselves, just by wedging. It's a formal exponential. And one thing that you do get, two things that you do get, one of them is that you use this action to relate different twisted differentials. So I started H being a closed two form, but if I use this exponential here by an arbitrary two form, I can actually relate the DH operator with any other DH for a three form in the same cohomology class. So it becomes clear that somehow what's important here is not the three form H itself, but just the cohomology class it represents. And if you do the same thing with the bracket, it transforms it and relates the H bracket with the DH bracket, the H plus DB bracket. So again, even also for the bracket up to an overall isomorphism of the whole thing, it preserves the natural pairing. The only relevant thing of H is its cohomology class. There is one other thing that T plus T star has. It's called the Chevalier pairing, which is the spin invariant pairing. I'm not going to be talking like somehow I mentioned the word Clifford algebra, and there is like a pairing that's compatible with the idea of there is a Clifford algebra hanging out here. There are actually a couple of different ways you can define it because there are some signs, and today this is the one. So if the Chevalier pairing between two forms, phi and psi, is going to be the wedge product of phi with the psi transpose. So psi transpose is when you pick psi 1, psi 2. Like if psi was a collection of one forms wedged together like this, then the transpose would be them wedged together backwards. So you flip the order of the factors of psi and then wedge them together and take the top degree part. That's the Chevalier pairing. The properties that it has is that if you were to pick x plus psi and act with that on both phi and psi, you just get the norm of x plus psi out. And if you try to act with a B field, the B field doesn't do anything, just gives you the same pairing. So that's the part of the spin invariance. This pairing is going to come up, like right now it's not so clear how it relates to the rest. It's going to come back in a second. Originally, when Courant and Weinstein were defining the geometry of T plus T star and discovering the Courant bracket, one thing that they realized that seemed to be important was this thing called the Dirac structure, which is a maximal isotropic involutive subbundle of T plus T star. So the idea is that the natural pairing of T plus T star is not, it is non-degenerate, but not positive definite or negative definite. It actually has mixed signatures, NN signature. So you can start looking for spaces which have precisely half of the dimension and are involutive with respect to the bracket. Examples are T star M is always involutive. And if H is 0, Tm is also in there, it's always involutive. And one thing that came later, so it was not like essentially it was Hitchens' contribution, is that you can describe Dirac structures in terms of forms as well. So using this relationship between brackets and forms, you can actually go back and if you give me a maximal isotropic, there is a unique rank one subbundle of the space of forms, such that if you have such that x plus psi is in D, if and only if it annihilates that form. So when you interior product of x and exterior product of psi, you get 0 for every non-zero form in that line bundle. This line bundle is called the canonical bundle. I'll give examples of that when we get to generalized complex structures, but it's something that in principle you can write for any Dirac structure. So for example, for T, the canonical bundle would be something for which whenever you contract with a vector, you get 0, and only if you contract with a vector, you get 0. So that would be the number 1, the constant function 1. And for T star, it would be something that when you wedge with a one form, you get 0 every time. So that would be a volume form. So the K would be the determinant bundle of the cotangent bundle. Uh, Looks like I repeated the slide. Yeah. Okay. Yeah. So one question is if you give me this canonical, but like what information do you have to give me about a line bundle in the space of forms for me to be able to say that this is the canonical bundle of a Dirac structure? And there are two things. One of them is that it has to be pointwise of a specific algebraic type, namely this one here. it should be e to the b, where b is a two form, and e to the b is like what I was writing before as well. Wedge with a pointwise decomposable form. So at that point, p omega should be the wedge of one forms. And that would take care of it being maximal isotropic, just having this algebraic form. And if you have a section of this bundle which doesn't vanish, you can actually check involutivity by this relationship between the Courant bracket and the exterior derivative. And see that D is involutive if and only if for every non-vanishing section, you can find x plus psi for which this holds. So taking the derivative of rho is just acting on rho by some x plus psi. So there exists one. And that brings us to generalized complex structures. They are like the complexification of this concept I was just talking about. So the original definition is not like the first one is not entirely obvious that it's going to be a Dirac structure, but there's three equivalent definitions and it gets closer and closer essentially. So the first one, which kind of justifies the name, is that a generalized complex structure on MH is a fiber-wise complex structure on T plus T star, which is orthogonal with respect to the natural pairing and whose plus eigenspace is involutive with respect to the Graham-Dorfman bracket. The part of being orthogonal with respect to the pairing, so that one is extended just by complex linearity on both entries. And whenever you have a complex structure which is orthogonal and for pairing under complex linearity, the plus eigenspace is automatically a maximal isotropic subspace. So you see right away that there's a relationship between this complex structure, which is just by the name, and its plus I eigenspace, which you call L. What's going on here now? I made it turn into interesting. Okay. Man, what's going on with my pen? Okay. I'll get out. So sorry for the technical difficulties. So you see right away that because J is orthogonal with respect to natural pairing, the subbundle L is going to be isotropic, and then you have the involutivity condition, and that makes it a complex Dirac structure. But it's not just any complex Dirac structure because L is the plus I eigenspace, eigenbundle of a real operator. So it cannot intersect its complex conjugate. So you also have this further condition here, which is L intersect L bar is 0. And there's a third definition, that's the one using the canonical bundle, which is that a generalized complex structure is going to be the same thing as giving me this line there. So it should be generated now by a complex form. So to keep track of real stuff, I actually write it b plus I omega, b being the real part of this complex form and omega being the imaginary part. And wedge of omega, where omega is a complex decomposable form. To check that L intersect L bar is trivial, you have to do this condition here, and that's why we have the Chevalier pairing. L intersect L bar is 0 is precisely this condition here of the Chevalier pairing being non-trivial, and it's a direct computation. I'm writing the wrong computation here because technically there's a factor here in front, but that's not very important because it should be non-zero. So as long as that is non-zero, you get that their intersection is trivial, and you got yourself at least pointwise complex structure on the sum of tangent plus cotangent. And then there's the integrability condition that comes just like the previous one as well. If you have a non-zero section of this bundle, what you want is that there should be a vector plus one form such that the h of your section is the vector plus one form acting on that form. So that's the integrability condition. Examples. At some point, you have to do them. If you give me a complex manifold, you can use the complex structure to create a complex structure on T plus T star. Because you want it to be orthogonal, you have to include this minus sign here. So that's an important one. If you don't put that, which would be what a lot of people would like to do, then you don't get an orthogonal transformation. Once you put that minus 1 there, you do get T01 plus T star 10 as being the plus I eigenspace, and you can check that that's involutive if and only if I is integrable. And the canonical bundle is what you normally call the canonical bundle in complex geometry, is the n0 sections of T star n, so n0 forms. So that's kind of how the different concepts translate for a complex manifold. If you have a symplectic manifold, you can also do the same thing. Now, because omega is a case difference. No, it's the same one. It's the same subbundle. So this thing here is supposed to be something which annihilates these vectors here. So if you give me a 0, 1 vector and I plug into an n0 form, I get 0 because it's plugging anti-holomorphic vectors in holomorphic forms. And if you wedge a 1, 0 form on an n0 vector, because I'm already at the maximum degree, then it also wedges 0. So this is indeed the line subbundle. There's a complex line subbundle in a space of forms which annihilates this space here. So it's the same K that we had before. And for the symplectic structure, what we do is that we think of omega as being a map from tangent to cotangent, because you can always plug in a vector in the first entry and you end up with a one form. And because omega is non-degenerate, that's an isomorphism. And then you can look at omega inverse going backwards. And now you write yourself this matrix here. So this is omega inverse sending T star to T. And this is omega sending T to T star. So this is written in the splitting T and T star. And because you put this minus here, it squares to -1. And you can go and try to describe the plus eigenspace. This one seems a little bit boring because essentially it's a graph. You have the tangent space and you just kind of lift up for every vector. If you just add a one form to it that depends on the vector to get your plus eigenspace. The canonical bundle, you can also just figure out. This is a weird one from the point of view of classical geometry because it's a form of mixed degrees, different from the previous one, which was just an n form. It is this formal exponential of omega, e to the I omega. So if you try to plug in a vector like something like this on that form, you get 0 because one time you get wedge, and the other time it just comes out of the exponential. So that highlights this thing that in generalized complex geometry, you should really not think of forms as having a fixed degree. You should really think of them as even and odd, and these exponentials appear all over the place. So exponential of a 2 form is all over the place. But that would be then the description of a symplectic structure as a generalized complex structure. You have the 3 different approaches, and here you have this extra thing that because the symplectic form is closed, d of e to the I omega is just 0, and that's a global thing. In the previous case, it was also true that if I was to pick this form here, d is at 1, d is at n, in local coordinates, d of that is actually 0. So locally, I actually have a closed form defining my structure, but if you try to patch them together, it might not even be the trivial bundle. So you might not even have a global form that trivializes the bundle. And even if you did have, it might be that it's not closed globally. For symplectic case, it's simpler and you just get a global, nowhere vanishing as closed section of the canonical bundle. There are non-trivial examples. So simple ones, you can, on C2, if you give me any holomorphic function, I can just write something like this, f of zw plus dzw. If f is non-zero, I can rewrite it in this way. And this is something of the form exponential of a complex 2 form. And the imaginary part of that complex 2 form is non-degenerate. So this is of symplectic type whenever you are not at a 0 of z and w of f. If you are at a 0 of f, then this term here disappears and you just have dz plus dw, which is the complex type of generalized complex structure. So you see that in C2, you can have these generalized complex structures which are complex at some points and symplectic pretty much everywhere else. So it's open dense symplectic and complex in a analytic subset. And you can check the integrability condition. I do it here. It's a simple computation, but I'll just skip that. Like you just check it by hand, and this is the vector that you have to use to check integrability. So it's something you can like explicitly do. One example that is of that form, you can start with C2 again and use the holomorphic function Z. That's the simplest holomorphic function that's non-constant that I can think of. Then your line, the canonical line is of this form now, d log z dw. And then you notice that, well, the w is not doing much. So the whole structure is invariant under translations in w. So I can take the quotient by z squared to get the w directions to be compactified. So instead of being on C2, now I am on C times T2. So the C corresponds to the Z coordinate. That one I cannot do away with it. But the W coordinate is supposed to be taken out periodic. I can write down this expression in polar coordinates. Oh, it's just an I. I don't know why there's a prime here. It's a mistake. In polar coordinates, you can write z is equal to r e to the I theta, and the w we kind of made it periodic because we take the quotient by z2, so it's just the sum of two angle coordinates anyway. And then you can write down what the imaginary part of this two form is, because that's supposed to be our symplectic form, and it looks like this: d log r d theta 3 plus d theta 1 wedge d theta 2. So the angle of the z coordinate gets paired with one of the angles from the w coordinate. It's not like the pairing is kind of a bit mixed. And you can go and compare that with what would be the standard symplectic structure on the product, d2 times t2. And again, for that, you don't have the mixing. So this is the z coordinates. You just have dr squared d theta 1. That's the standard symplectic form in R2 in polar coordinates. And here you have the other one that's just the symplectic structure in the torus. And then if you stare at this for long enough, and maybe not even all that long, one thing that you notice is that there is a symplectomorphism between these two structures here, which is non-trivial. So if you were to ignore r equals to 0, so remove that and just look at the annulus, then you can find a symplectomorphism that pairs theta 1 tilde with theta 3 and theta 1 tilde, theta 1 with theta 3 tilde and preserves theta 2. So what that means is that if you find yourself a symplectic torus with trivial normal bundle somewhere, you can always remove it and glue back one of these type changing generalized complex structures. The only thing is that you change your manifold when you did that. But that would be a way to produce non-trivial generalized complex manifolds. You just have to find yourself a symplectic manifold with a torus with trivial normal bundle. And if you start looking into the theory, there's a lot of those in 4 dimensions. So it's not, we're not asking for something far-fetched here. In fact, that was how it came to the first like non-trivial examples. Given a symplectic form manifold with a symplectic torus with trivial normal bundle, the manifold obtained by doing this switch that I just mentioned, which is called the C-infinity log transform, admits a stable generalized complex structure. First example, one looks at like K3 surfaces. Some of them are elliptically fibered. If you do the surgery, you get 3 CP2s and 19 CP2 bars. And the weird thing, like before that, I never thought about it, but connected sums are not good operations for complex or symplectic structures. So if you start doing connected sums of symplectic manifolds, typically you just get manifolds. You don't get something with decent structure. And here, this 3 here, the fact that this 3 is actually more than 1, tells you that this manifold is not complex and is not symplectic, but we just put a generalized complex structure on it. So that was the first example of a generalized complex manifold, which is not complex nor symplectic, and that's one we can prove. And it's already in the smallest dimension in which it can happen. Once we find that example, then we kind of got excited about the whole thing and went on trying to find more. So K2 is the K3 is what we call E2, is the second elliptically fibered complex surface. The first one is CP2 blown up at 9 points. But you have a whole family of them, and you obtain them by doing fiber sums. So start with E1 and do fiber sums of E1 of itself as many times as you like. And those are these ENs. And then again, if you do that surgery on the EN, you end up with this many CP2s. And then we started studying, okay, got all the CP2s, but there was also a collection of CP2 bars, a large number. And then we actually managed to study like what happens if CP2 bars, can we blow them down? Like differentiably, you always can, but then there's also a generalized complex blow up and blow down. and you could actually blow them down as many as you like. So you end up with like here M just has to be positive, non-negative, and all these manifolds they have generalized complex structures. And here you have already the first coincidence that in this family here of manifolds which are connected sums of CP2s and CP2 bars, you're getting that they are generalized complex if and only if they are almost complex. Torres went on and studied the same thing in more detail with S2s cross S2s and came to the same conclusion. Connected sums of S2s cross S2s are generalized complex if and only if they are almost complex. And we continued that trend and also started putting some S1s cross S3s there. And again, they are generalized complex if and only if they are almost complex, but there is one extra thing that somehow we are getting positive Euler characteristic only. That's something that Torres observed early in the story. That's we are getting positive Euler characteristic, but never negative. And then became a bit of a question. Are there stable generalized complex manifolds with negative Euler characteristic? This is a relevant question because if you want to try to find an example of something which is almost complex but not generalized complex, you'll do well looking into the ones with negative Euler characteristic. It seems to be that they are much harder to become generalized complex. And that's one of the paths that we are taking nowadays, me and my student Bas. So that's how we got to produce a lot of generalized complex manifolds without complex or symplectic structures. Changing gears here, not a different topic. One of the features that I mentioned is that once you put everything in this generalized framework, different concepts that had already appeared in complex and symplectic geometry, they get unified. So you start getting things that specialize to known things. One of them is the double complex. So let's try to talk about that one. So what happens is that if you have an almost generalized complex structure, it decomposes the space of forms in the following way. So you start with the canonical bundle that we had before, and you hit it with the complex conjugate of the plus I eigenspace. So you hit with the exterior power of the minus I eigenbundle. Then you get these subbundles called UKN minus 1, and they together give you a direct sum decomposition of the cotangent bundle. So algebraically, you always have that. If you are in a complex manifold, for example, what would these UK spaces look like? They would be the spaces for which the sum of holomorphic and anti-holomorphic, or P minus, the difference between holomorphic and anti-holomorphic wedges is constant. So the UKs, again, just as before, they are not like K forms or anything like that. So they are mixed degrees, like they are even or odd, but that's it. And for example, the U0 would have the 0, 0 forms, all the functions. The 1, 1 forms, the 2, 2 forms, the 3, 3 forms, they're all together there forming the space U0. So compared with complex manifolds and the general theory of complex manifolds, we are losing a little bit of information because we lost the degree. So you only know the difference of P minus Q, you do not know P and Q separately. One thing you can try to do is try to study the question of integrability, and you can define this Nyinghaus tensor. So if you give me 3 sections of L bar, you can take bracket of 2. If your structure was integrable, then this bracket would lay back on L bar, and L bar being isotropic, this pairing here would be 0. So if the pairing is not 0, it indicates that this bracket here has an L component, and therefore L bar is not involutive, and your structure is not integrable. So integrability is actually the same thing as having this operator n here being trivial, 0. And similar to the Nyinghaus tensor for almost complex manifolds, this is a tensor instead of being an operator. So it's actually a section of wedge 3L, which is kind of nice because it's just fully schizometric now. The Nyinghaus tensor cannot be fully schizometric because it takes values like the usual one in almost complex manifolds. It picks 2 vectors and spits out a vector. So there's no way that that can be fully schizometric, but here it actually is.
Can I ask you a question, more curiosity? So, is it true some generalized version of Nylander-Nirenberg? So is it true that if you have n equal to 0, you have spatial coordinates or not?
Yes, it is true. It's not as sharp as one might like it to be. So the statement, there are two of them.
Okay.
One of them is if you are at a regular point, so that the type is not changing, so the structure has constant type in the neighborhood of that point, then Gualtieri proved already in his thesis that then the structure is a product of complex and symplectic.
Mm-hmm.
So you can actually find complex coordinates and RB coordinates and get your structure to really be just a product of the standard complex and standard symplectic structure. And that proof actually is just like using Newland-Nirenberg. Actually, Newland-Nirenberg proved something a bit stronger than what we normally quote, and
Mm-hmm.
then applies directly to that situation to get the conclusion. Uh, if the type is not constant, so if you're at a point which somehow has a type bigger than the nearby ones, then you have to do something else. That's a theorem of Michael Bailey, which is the local form for generalized complex manifolds, which is that they are always the product of something symplectic and a holomorphic Poisson structure. So you can always use a holomorphic Poisson structure to deform your your complex structure. That's like earlier when I was writing that holomorphic function f, essentially I was in disguise doing a holomorphic Poisson deformation. Um, so that's one way. If you have a holomorphic Poisson deformation, you can kind of change the type. And then every generalized complex structure is always equivalent to the product of a standard symplectic structure and a holomorphic Poisson structure, which vanishes at the point in question. The only thing that's not fully nailed down by this result is that it could quite well be that different holomorphic Poisson structures would still yield equivalent generalized complex structures. So it's
Okay.
not there's no claim about that there needs to be a biholomorphism of the data that I just described.
Okay. Thanks.
Mhm. And it's good to actually look into what the exterior derivative, the dH, does when you have just an almost. So like how does integrability come about? So I have already introduced these UK spaces, which are the decomposition that you get when you hit the canonical bundle of L bar. And you can see that the dH decomposes into four operators. It's similar to what happens in an almost complex manifold. If you look at what it does at PQ form, it has four components. The immediate two here are differential operators, which are like the del and del bar operators for complex and almost complex geometry. And you see that the ones that actually shift the degree the most, that go plus or minus 3, those would be the components of the Nyhaus tensor. So those are tensorial. And if they vanish, like the vanishing of this maps is equivalent to integrability of the generalized complex structure. So D has only two components if and only if J is integrable. And that's one way to get around your head around, like if I somehow get my hands on a generalized complex structure, what would I know to start with? So for example, if I was to focus on the UN, which sits somehow all the way here at the end, then there's nothing on the right. So here, from here onwards, it's just trivial spaces. And I would hit it with DH, and then in principle, it could land into UN minus 1. And it could land in UN minus 3. And if I want to know if my structure is integrable, what I have to do is to focus on this component here, the one that decreases the generalized complex grading by 3, and check if that is 0 or not. So that's an alternative way instead of doing brackets and pairings and so on, because some people don't like to take the brackets of vector fields. You can also check integrability using the exterior derivative on forms. There's another differential that's hanging out here, which is the Lie algebraic differential. So the idea is that this L and L bar, they have like they're closed under the brackets. That was the involutivity condition. And because of that, you can just pick these formulas they have for the exterior derivative and actually define also an exterior derivative on their exterior algebra. So this is something that you can just go and define. It's similar to how the Lie bracket on vector fields defines an exterior derivative on forms. You can use the Lie bracket on L to define an exterior derivative on sections of L bar. Because the Lie bracket satisfies the Jacobi identity, the Courant bracket satisfies the Jacobi identity on isotropic spaces, you get that this operator squares to 0. And in fact, there's a relation between this del bar operator that was just introduced earlier in this component here, and this Lie algebraic differential that I'm describing now, which is that either of these two things are the same equation written in two different ways. that if I want to do, the first one is written as a Leibniz rule. So if I want to do del bar, and here I have a section of L bar acting on a form, then I can either take the DL of the section of L bar and leave the form alone, or jump over, get the appropriate sign change, and apply the del bar that I have to the form. So the DL and del bar together have some sort of Leibniz rule. And same thing, but stated slightly different, is that the graded commutator of the operators del bar and alpha, so alpha acts by contractions and wedges, del bar acts because it's a differential operator. So the graded commutator, it's the same thing as taking dl of alpha and acting with that on phi. So it's the same equation with this term here sent to the other side. So you get to choose, but that's like a way that these things get related. So you have the del bar, which is the usual double operator. You also get the Lie algebra operator out of it as well. Examples. If I do complex manifold, this space is UK, as I already mentioned, is the sum over P minus Q equals to constant K. So you pick forms of different degrees and just keep track of the difference between holomorphic and anti-holomorphic degrees. And that's what makes your UK subbundle. D is the sum of del plus del bar, and that's really the usual del plus del bar from complex geometry. L bar we already described as being T10 plus T star 01. So the exterior algebra of L bar, the thing that I would like to use as Lie algebroid, is the sum of the exterior algebra of T10, that tensor the exterior algebra of T star 01. So this guy here is a holomorphic bundle. So I can actually define a del bar operator on that bundle, and that's the Lie algebroid differential operator. It's just the del bar, and the del bar increases the form degree, this part here. So it's just saying that's well defined because you have a holomorphic vector bundle there. So the L is really just the del bar that you have defined because this thing here is a holomorphic vector bundle. So that was reasonably nice because all these concepts that we kind of coming out of generalized complex geometry had a corresponding analog in complex geometry. In the symplectic geometry is a little bit funny because the one thing had already come about, which is this symplectic adjoint. So that one had been encountered already back in the 80s, which is a way to twist the exterior derivative using the symplectic structure. When it was introduced, it was really called the symplectic adjoint, and it was thought of as an analog of the adjoint of the exterior derivative with respect to a metric. So it was like Laplacian, symplectic harmonics. And somehow the analogy that they got was slightly wrong because the operator was correct, but it was made an analogy for the metric, not with a complex structure. Because we can find these operators reasonably easy, you can actually write down the commutator of D and the Poisson bivector. You can also write down the del and the del bar. These are a little bit funny. They had not come about before. They contain the same information as D and delta, so there'll be little sense in writing del and del bar. And they have this feature that del, in the symplectic case, decreases the degree by 1. So D plus I delta increases and decreases the degree. So it really messes up with the degree of forms, and people would not have written that for without a good reason before. The decomposition into UKs is something that had not appeared either. It's a computation one has to do, and it ends up being something like this. Like it's essentially the same thing as the decomposition of forms by degree. But now I have to apply this automorphism to the space of forms. I first do a whole bunch of contractions by the wedge, by the inverse of omega, and then I do a whole bunch of wedges with omega again, and then I get this space UK. This thing's it's an invertible map, so it's an overall automorphism. So essentially UKs, this space is UK in the symplectic case, they are just equivalent to the decomposition of forms by degree, but it's funny because they're twisted by the symplectic structure. And if you want to know what the del and del bar operator do, because somehow they are a bit mysterious, they are supposed to increase and decrease the k degree of this UK of these bundles here. And when you write down in this particular expression, so using this isomorphism here, you see that the del is just the same thing as D under the isomorphism, and the del bar is the same thing as the symplectic adjoint. So in a way, they don't really bring a lot of new information here. It's everything like D and delta just packaged in a slightly different way via this global isomorphism of the space of forms. But it's good to know that this isomorphism of the space of forms is hanging out there, You see here, for example, that there's some shift in degree. It's not k goes to k. It's more like n minus k goes to k. So like it reverses the order, recenters. So it's a bit of a messy one when you look at the indices. And that's something that can be puzzling to people at times. I would like to talk about deformations, but I see that the time is kind of running short. Uh, I guess we should have a break. So maybe since this is like a natural point to kind of have a break, let's say we have a break for as long as the chair says the break lasts, and then we continue. Or you guys do it without
Okay.
break.
So first of all, thank you for this. So let's see if people have some further question for you.
In the introduction, you mentioned that there are generalized G2 and spin 7 manifolds. Are these generalizations of manifolds with holonomy G2 or like just G2 structures?
It's more like G2 structure than holonomy. The notion of holonomy, it has not really been defined yet. I have a student who's currently working on this, and I guess the only thing I can say is that holonomy in the generalized world is more complicated than holonomy in the usual case. So right now we don't even have a definition of the holonomy of a manifold, of a generalized manifold with a connection, like or generalized Riemannian manifold is. We don't have that. Is even a bit worse because in what allows us to talk about holonomy in Riemannian geometry is that there is a unique connection which is metric and torsion free. Once you go to the generalized world, there is not such a thing. There are many, and then even which one should you use to talk about the holonomy becomes a question. So not only there are many connections, and holonomy is probably not going to be canonical to the Riemannian manifold that you have, but also the definition of holonomy is not quite out there. So people did more like G2 structures in the sense of this looks an awful lot like what you'd have in a G2 manifold. The definition of G2, generalized G2 was in terms of parallel spinors. It was a 7, put by hand. It's a parallel 7 manifold with 2 parallel spinors and then generalized spinors. And eventually the result was that if you have a compact generalized G2 or generalized spin 7, then you are in fact G2 or spin 7. So in the compact world, you don't get new examples, which is a bummer. But that's really in terms of having the correct tensors, the correct properties, not the holonomy classification anymore.
Okay, thank you.
Okay, so I guess if we don't have any further question, we should have a break. I would say 5 minutes. If you need more, we can have it longer or whatever you need.
I'm fine with 5.
Okay, so
Here, people are very considerate to students, and then they keep on insisting like 10, 15 minutes. It's shocking. You have no idea how hard. I'm very shaky by the end of the day just because I keep on drinking coffee for 15 minutes, you know?
okay, yeah, let's do 8 minutes then.
Okay, so back at 10 past.
Yeah.
Okay, I'll just grab myself a coffee and be back here.
Okay. Thank you.
See you in a bit.
Maybe I should pause the recording.
Yeah.
The recording. And let's continue with
Okay,
introductory talk by Gil.
thank you. So let's just talk a little bit about deformations of generalized complex structures. That's a normal question that once you introduce a geometric structure, one of the things that you'd like to know is does it deform? Or can you describe its moduli space? So how do you set up the question? So I'll only do part of it. And the idea is that you can actually split, not in T plus T star, that's normally what I do when I do this kind of graph here, but you actually decompose the T plus T star into L and L bar. And you know the L fully determines the transcomplex structure. So to deform the transcomplex structure, what you want to do is just move this thing here up or down a little. So that's what you want to do. At every point, you move it a little, and then you got yourself all the nearby. Like that's a way to describe any nearby one, just by adjusting how much you go up or down. So what you want to do is just describe nearby spaces which are still maximal isotropic. The way to do this is that you pick the graph of a function. So this should be the things of the form. I'll just write here v plus epsilon of v with v in L. So that's what it should be, and the epsilon should be a map from L to L bar. And because we have the natural pairing and L bar is naturally isomorphic to the dual of L, this is the same thing as saying that epsilon is actually a 2 tensor. It should be something tensor 2 of L bar. One condition is that this new space that you're producing here, which we'll call L epsilon, should be maximal isotropic. So to do that, it's an algebraic condition that imposes the epsilon itself has a specific algebraic form, so it cannot just be any 2 tensor. It has to be a skew-symmetric 2 tensor. But once you do that, you know that you describe yourself another subbundle sitting inside the complexification of t plus t star, which is maximal isotropic. And once you have the L epsilon, you also know what to do with the other one, because the deformation of L bar would be just using the epsilon bar. So there's like a unique way to do the formation of L bar so that you still get the minus I eigenspace, which would be the complex conjugation of L epsilon. So this epsilon here, which is just a section of wedge 2 of L bar, has all the information you need to define and describe nearby structures. And you can play around and see what's the canonical bundle. So you already had the canonical bundle for L before, and now you have this epsilon hanging out, and there's a simple thing you have to do, which is just hit the canonical bundle with the epsilon itself. And that gives you the canonical bundle of this new structure. In fact, not just for the new structure, for the canonical bundle, but in fact, the UK epsilon is going to be the epsilon UK. So that's just something that you get for all of them. So there's a clear linear algebraic relation between the deformed spaces and the previous spaces once you have this. And then the only question is integrability. Recall that before I had this kind of picture that I had un all the way up here in principle, and now un epsilon. And when you take the exterior derivative, the dh, it will have a component going down here. This is del bar. That one is always there, cannot do anything about. But the one that governs integrability is the one that jumps up 3. So it goes all the way up to here. That would be the Nyhaus tensor. So you want to compute, like, what's the condition on epsilon for which this thing here vanishes? So what's the relationship between this n and the parameter epsilon that you're using? So I'm just writing it long-handed here. So to say that this component that vanishes would be the same thing as saying that d of epsilon rho being a section of the original canonical bundle, lands here, which would be, it has this form here. And having this form here is the same thing as, it's not the same x plus xi, but it doesn't matter. It's just some x plus xi that change between one and the other, but it's having this form here. And then what you can do is apply e to the minus epsilon on both sides to end up with this kind of equation here, which is e to the minus epsilon dh epsilon should actually be in un minus 1 for the original structure. So what we did here was that instead of having the spaces that I'm considering be varying according to the parameter epsilon, once I do this business of sending this e to the epsilon back to the other side, I have a differential operator that depends on epsilon, but the composition of the space that I'm using is not constant. So that's a better way to phrase the whole thing. So what I want is to find epsilons for which this thing here holds. If I conjugate dh by epsilon, apply to a section of the canonical bundle, I should get something un minus 1 instead of something that also has a component in un minus 3. And the proof, like I'll just show it because it's kind of cute. How do you deal with this kind of question? So there is an algebraic identity that we use all over the place, and I'll only show the strict ones, so pay attention. What you notice is that if we were to expand these exponentials into their power series and start grouping together the terms that have epsilon, you'd see that there's two possibilities for terms that have degree 1 in epsilon. Either you take one from this term here, which would be an epsilon on the right of dh, or you have one from this term here, which would be a minus epsilon on the left. So you have a d epsilon minus epsilon d, and that is this graded commutator that appears here. If you start looking at the quadratic term, you see that you can have some epsilons on the right and some on the left. And every time you have an epsilon on the left, it appears with a minus sign because of this thing here. So that means that you are always doing this graded commutator, which is that when you have two epsilons on the left, you get a plus sign. If you have one epsilon on the left, have a minus sign. So the odd number of epsilons on the left gives you a minus sign. And then just count it and you start getting these factorials here, which are the factorials of the exponential map. So you end up with the degree 2 epsilon term would be this one, the degree 3 would be this one, and just keep on repeating with more and more epsilons. And that would be this operator that we are writing here. So that's just a matter of like trying to expand the exponential and grouping together the terms by degree on epsilon. Then what we notice is that this term here, with the double bracket, double commutator, is precisely how we defined the Courant bracket earlier. So whenever you see the age of this double commutator, say, hey, Courant bracket appeared, and then you get it here. So this is the definition of the Schouten-Nyhaus bracket, Courant brackets in general. So this is just by definition of the Courant bracket as a derived bracket, and that's why I think that this description is more becoming, it's a more conceptually better than just writing down some symmetric brackets. And then similarly, this term here, just with two epsilons, is already the Courant bracket. And then there's one extra epsilon that you still have to put here. And then you said this is a commutator of a graded commutator of the action of these guys here. And this one is in wedge 2 L bar, wedge 3 L bar, and this one is in wedge 2 L bar. And when you graded commutes, you see you'd get some sort of pairing between them, but the L bar is isotropic. So this term here, just because it's all in L bar, it becomes 0 right away. And so are all the next terms in the sum. So even though in principle could have like a long sum here, in fact, it only has 3 terms. It's dh commuted with epsilon once, and the Courant bracket of epsilon itself. And then you can decompose dh into del and del bar. So here del, del bar, del, del bar. And we use that identity that the commutator of del bar with an epsilon was essentially how we defined the Lie algebraic differential. And this last term with the bracket there. And then start looking which ones of these actually would change the degree by 3. So go from un to un minus 3. So this one here would send un to n plus 1. This one here goes to n plus 1. This one goes to n minus 1, because that's what del bar does. It decreases the degree just by 1. The del increases by 1 and the epsilon decreases by 2. So this one also just sends to n minus 1. And these guys here at the end are the ones that actually would pick un and give me something un minus 3. So this thing here has to vanish. If it vanishes, I got myself integrability. If it doesn't vanish, then I don't. So that's the integrability condition you get there. You get the Maurer-Cartan equation appearing. And that was something that was known before. This is like a cleaned up version of what had already been proved by Liu, Weinstein, and Xu in 97. And Gualtieri kind of rephrased it in generalized complex terms. But the deformed generalized complex structure J epsilon that we introduced earlier is integrable if and only if the parameter epsilon satisfies this Maurer-Cartan equation. And that's kind of the trick, is to, which is more the relevant part, was that we kind of transform first the integrability condition into an operator acting on a fixed space, and then we study the operator by expanding power series, for example. So that is, I think, the end of the first part. And I'll just move on to the next one. So generalized Kahler and SKT geometry. So let's try to put a metric in now. So I do not know how many of you are familiar with SKT structures. I don't know how many of you are students of Anafino. So this is something that at first is not generalized complex at all. It was something that already existed for several years. The idea is that instead of having a Kahler manifold, you pick something with a connection for which the matrix is parallel, the complex structure is parallel, but the connection is not the Levi-Civita, is one with skew symmetric torsion. So that's what they call a KT structure, Kahler with torsion. And if you require that this torsion is actually closed, then it's a strong Kähler torsion. And it's equivalent to having a Hermitian structure, so I is integrable in a compatible metric G, for which when you form the corresponding symplectic form, you get DDC of omega is equal to 0. And the age that we have here that will be the torsion of the connection is this DC of omega. So these are equivalent ways. So eventually we are looking now for a pair of complex structure and metric for which the candidate symplectic form is not closed anymore, but it's DDC closed. Kähler manifolds are examples of SKT structures. Every compact even dimensional Lie group is an SKT manifold, and if you're not a torus, then it's not Kähler. So there's many known Kähler examples of SKT manifolds. Every compact complex surface is SKT, and only I'd like to say half of them, but only the ones with B1 even admit Kähler structures. And there are some advanced examples like instanton moduli spaces are SKTs. Pino, Parton, and I forgot the third person, they gave a classification of which 6 new manifolds admit SKT structures. There are some. I'll get to their name in a second. So SKT manifolds exist, and it's a genuine generalization of Kähler manifolds that have examples of non-Kähler SKT manifolds. Back then, when I was working on this topic, there are all these nice properties of Kähler manifolds, namely they have a decomposition of cohomology, there's this Hodge theory stuff. The Fröhlicher spectral sequence degenerates, they are formal, and they have unobstructed deformations. And essentially, in one go, Fino, Parton, and Salomon was the third one, proved that the SKTs do not have any of these properties. So in one go, one paper, new manifolds, and you get that like none of this works. If I am to be fair, so the unobstructed deformations for Kähler manifolds are typically phrased like this. If I deform the complex structure, I can also deform the symplectic structure so that it remains Kähler. So that's a stability theorem by Kodaira. But if I wanted to think of it in generalized complex terms, I could also think, well, if I deform the symplectic structure, can I also deform the complex structures that it remains Kähler? And the answer for the second question is not. So deforming the complex structure first is good, deforming the symplectic structure first is not good. So technically, it's not really stable, so I should put like a cross there to say that even in the Kähler world, the deformation theory, especially if once you get unobstructed deformations, requires more hypotheses than just that. And typically one that people like to put would be the Calabi-Yau condition. Then they're both in the same footing as well. If you look at SKTs from the generalized complex point of view, then what we get is that some of this improves a little. So the composition of cohomology, we actually get one of those, but it's not the usual de Rham cohomology. So that one, there's no way. But you do get a decomposition of cohomology by using generalized complex point of view. You can develop Hodge theory, so the composition, like identity of Laplaces, that type of thing. A spectral sequence will degenerate at the second page, also because you have the decomposition of cohomology. Like there's an identity between the double cohomology and DH cohomology. Formality is something that, as far as I know, you cannot get. There's no formal object associated to an SKT manifold, not yet. And okay, deformations remain obstructed, but they were already obstructed for Kähler anyway, so maybe it's not a surprising thing that it remains so. So that would be what I'd like to try to get to. Let me see if there's anything else. Yes, you could ask the same questions for generalized Kähler, and for generalized Kähler, the crosses become yellow, so it's still not true, but essentially under some hypotheses, you can still get a formality result, and you can still get an unobstructed of deformations result. But for the SKT case, if you don't ask them to be generalized Kähler with the generalized Kähler hypothesis that you need for the second column, then it's not. So SKT is slightly weaker than generalized Kähler. So the main insights that we use to get those results is say that SKT structures are also generalized complex structures. So they also sit on T plus T star, which was not an obvious thing to start with. And you can start describing the failure of integrability. So the nine-house tensor that I was talking about earlier that governs whether or not a generalized complex structure is integrable, it comes in here as well. And if you start studying how it becomes zero, how it becomes non-zero, it's a helpful thing to get these results. So for the second part, hopefully this is correct. I'll talk about metrics on T plus T star, the nine-house tensor and intrinsic torsion, tell you a little bit about Hodge theory, and hopefully I get some information, although when I look at the clock, maybe I won't. So generalized metrics, before I was always doing generalized complex structure, so something whose square is -1. And now we have something similar. So again, a bundle automorphism of T plus T star, but now instead of having square -1, it gives me something positive definite. So we require that it's orthogonal, self-adjoint, and give me something positive. The orthogonal part tells me that the inverse is the transpose. The self-adjoint says the transpose is G, which means that G squares the identity. So instead of squaring to minus the identity, which was the case for the generalized complex structures, now it squares to plus the identity. And G is determined by its +1 eigenspace. So it has eigenspaces plus and -1. The pairing, these eigenspaces have to be orthogonal to each other. So if you know which one is the +1 eigenspace, you have an orthogonal complement has to be the -1 eigenspace. And the idea, if you say, what does a generalized metric look like? So if I just had an actual metric, I could think of it as a map from Tm to T star m, just like what I did with the symplectic structure. And then a generalized metric that would go with it would be something like this. G, oh, wrong, would be G inverse G 0. So this would be one way to produce a generalized metric. You just put G in the off diagonal, since T plus this is T star, G inverse goes backwards, and then you get yourself a generalized metric satisfying all these properties there. Once you have a generalized metric in an orientation, you can actually define a Hodge star operator, which I realized I did not actually write down the definition. Let's say that we understand it exists. I can tell you what it looks like later. We use the Chevalier pairing to get the positive definite part of it. So in principle, because I'm using Chevalier instead of just wedge product, remember the Chevalier had this transposition. It was essentially taking the wedge in the top part, but has this transposition as well. And because you have the transposition, it's otherwise the same thing as the Hodge star. I change some signs. Every now and then I change a sign. So on 0 forms, I don't do anything. On 1 forms, I don't do anything. But on 2 and 3 forms, I change the sign. On 4 forms, I don't do anything. 5 forms, I don't do anything. 6 and 7, I change the sign again. So the way that the Hodge star now behaves, that if you square it, it just gives you a constant that only depends on the dimension. It doesn't depend on the degree of the form anymore. That's different from the usual Hodge star. And because I have this operator that just squares to some number depending on the dimension of the manifold, I can decompose the space of forms into the eigenspaces of this Hodge star operator that we have here. I don't have like a systematic way of doing that, like the best systematic way. So the idea is that I is the root of -1. So I'll call the ones that have this eigenspace the self-dual forms, and the ones that have this eigenspace the anti-self-dual forms. And this particular choice of signs is that in 4 dimensions, the space of self-dual forms that I'm describing here would agree with the space, would contain the space of self-dual 2 forms that you'd have there. And anti-self-dual would contain the space of anti-self-dual forms in a 4 manifold. So that's kind of why is the minus here, since like sometimes I even have powers of I, right? So it's not in dimension 8, they would be backwards. So what I'm calling self-dual would be normally called anti-self-dual. So we have the metric, we have the Hodge star. If I want to do a generalized almost Hermitian structure, what is it? So I would like to have a metric and a compatible complex structure, all generalized complex structure. So that's what it is. The compatibility condition, so this is the generalized metric, this is the generalized complex structure, and the compatibility is that they should commute. So that's what plays the role of the usual compatibility for Hermitian structures. That's I and G behave in a way that gives us the symplectic form. If they commute, then you do get that this guy here, J2 equals to this, will satisfy that J2 squared is equals to G squared times J1 times J1 squared. The first one is the identity, the second one is minus the identity, so just get minus the identity. So you see that J2 is squares to minus the identity, and it's then an almost generalized complex structure. It might not be integrable. That's the only thing. So the plus eigenspace might not be involutive, but otherwise satisfies the correct linear algebraic conditions. And not only that, but J1 and the J2 commute. So not only I have the plus eigenspace for J1 and the plus eigenspace for J2, I can diagonalize them both at the same time. So I actually can decompose T plus T star now instead not just as L plus L bar, but the sum of four spaces. And I'm using the 1, 0, 0, 1 here to indicate the plus I minus I for J1. So V10 is something that's in the plus I eigenspace of J1, and V01 is something the minus I eigenspace of J1. And the pluses and minuses indicate the eigenspaces of G. So in V plus, you're in the plus 1 eigenspace of G, and the V minus is in the minus 1 eigenspace of G. So you do get this decomposition here, that the exterior algebra of the manifold actually decomposes into the PQ decomposition for J1 and J2 intersected. So because of this commuting relation. So you get a bigrading whenever you have a generalized almost Hermitian structure. If these structures turned out to be integrable, J1 and J2, then you'd call that a generalized Kahler manifold. If you actually started, for example, with just a usual Hermitian manifold, almost Hermitian manifold, no generalizing here, then that's integrable, is a generalized scalar if and only if it's scalar. So if you start with Hermitian manifolds, the generalized scalar condition and the Kahler condition would agree. And here is a picture of what the UPQ decomposition now looks like. So this thing here, for example, is supposed to be the canonical bundle for J1. This one here is supposed to be the canonical bundle for J2. And all the non-trivial spaces they fit in this diamond here. So if you have a section of V plus 1, 0, it goes like this. While V plus 0, 1 goes backwards, and V minus 1, 0 goes this direction, and V minus 0, 1 goes in the other direction. So you not only have the decomposition, but you can see, like, if you use the splitting of T plus T star into these four spaces, you see how each one of them moves you in a different direction in this lattice. If I had an actual Hermitian structure, then you see that the compositional forms of this wedge 0, 0, 0, 0, 1, etc. This is just the PQ decomposition for the complex structure. And when I want to see it from this generalized complex point of view, all I have to do is to hit with that symmetry that I had mentioned earlier. Like the symplectic circle gives me a whole twisting of the space of forms. And if I just hit the standard decomposition, PQ decomposition for a complex structure by this automorphism defined by the symplectic structure, I get the spaces UPQ for symplectic, for almost Hermitian structure, seen as a generalized almost Hermitian structure. So that's this interesting feature that I have a relationship between what's going on in the generalized complex world and the just Hermitian world by this overall automorphism of forms. One feature that you get also is that there is a relationship between the plus I, between the Hodge star and these operators J1, J2. So the Hodge star is actually given by this thing here. So on UPQ, the Hodge star is just multiplication by I to the P plus Q, because you get a P, I to the P out of this guy, and an I to the Q out of this one here. So one feature that you get in this generalized complex world, which is somewhat different from the usual Kahler identities type of thing, is that now the Hodge star is really simple. If you have taken a course in complex geometry, or if you have read a book, maybe you remember this Hodge-Riemann bilinear relations, which is something about the an integral being positive definite in certain spaces, and it's always like the space of primitive forms, PQ type, etc., with a -1 to the P minus Q, etc. So all that's taken care of by the correct choice of signs. And now the Hodge star, which is something that gives me positive definite things, is just this this thing here. On UPQ is just I to the P plus Q. So you actually see that the value that the Hodge star has only depends on the sum of P plus Q. So if I also go back here to my the composition that I was writing earlier, if I look at this diagonal here, P plus Q is constant. It's equal to 3. And in this diagonal here, P plus Q is also constant, but now it's equal to 1. So you see that it will be alternating because the value of the Hodge star is I to the P plus Q. So you see that one of these diagonals is going to be in one of the eigenspaces, and the other diagonal is going to be in the other eigenspace, and they keep on alternating like that. So if I was to describe here the self-dual and anti-self-dual forms, they are nicely compatible with the generalized complex decomposition of the space. So in this case, the red ones are self-dual forms, the sum of all of them, and the green ones are anti-self-dual forms. And yeah, so that's a little bit better than just having even and odd, because now I have even and odd, and I have self-dual and anti-self-dual as well, and they're all nicely compatible with the Kahler, the generalized complex decomposition. Recall that we had also this nine-house tensor in terms of taking the bracket of sections and pairing them again. Integrability was n being equal to 0, and in principle, for one generalized complex structure, if you do not know if it's integrable or not, you have 3 different maps. It picks a section in UK and can increase the degree by 1, that's the del operator, can decrease the degree by 1, that's the del bar operator, and have these components which are the nine-house tensors that can increase by 3 or decrease by 3 for J1. So that's something that you can have. If you have just one generalized complex structure, the index K that you're using can increase or decrease by 1 or 3. So there are 4 options that you get there. If you have a pair of compatible structures, then you can see that it's going to be 4 squares. So you have a lot of arrows. So this is where you can get DH. So if I apply DH to something in UPQ and see where does it land, there'll be this middle guys here, which are differential operators. So the delta plus, delta minus, etc. So for example, delta, there are these guys here in the middle. And these guys here on the side, for example, they are the ones that change the P index by 3. So they measure the lack of integrability of J1 together, all of them together. So the N plus, N3, N4, and N minus, all of them together are measuring the lack of integrability of J1. While these guys here measure the lack of integrability of J2 because they are the ones that increase the Q by 3. And you see, for example, that if this one here is non-zero, then neither J1 nor J2 are integrable. So whether they're integrable or not is not an independent question. So there's like a common thing there that if one of them is non-zero, then automatically neither of them is integrable. So if J1 is integrable, you kill off, of course, these arrows are related by complex conjugation. So if J1 is integrable, then these terms here would all disappear, and so would these ones, because they're just complex conjugates, and you get a much more manageable diagram, which is just this. So you can see that once you have one integrable generalized complex structure, so say you are in a Hermitian manifold, the question of whether or not the second one is integrable, so whether you have a symplectic form or not, is governed by these 2 tensors that you have here, the N1 and N2. And their complex conjugate down here. But essentially, you are asking, are N1 and N2 0? So if N1 and N2 are 0, then you'll be in a situation which have an integrable complex structure, and the integrable symplectic structure will be Kahler. Now we are in the generalized world. So if the N1 and N2 are also integrable, then you get a generalized Kahler. So that is how the exterior derivative decomposes in a generalized Kahler manifold. Out of the 16 components it could possibly have, it only has 4. All the other ones vanish. And that's a generalized Kahler manifold for you. So it makes sense to look into these tensors. So they are, I call them the intrinsic torsion of a UN cross UN structure, because of work of Gray, Hevel, and so on, kind of is reminiscent of that idea. And the question is like, what if some of them are 0 but not all? Like, are there special structures that you're getting once you have some of them vanishing? And The interesting thing, it's a computation that one has to do, so I'm not going to do it here, but like it's really down to just writing our computation. That if you have an SKT structure, so you have let's say it like this, G, I, and omega. So that's the omega that's defined by G and I, and dc of omega is equal to H. Then you use this H in your current bracket, and you'd see that the plus I eigenspace of I on the plus one eigenspace of G, so you kind of make the commuting structures, would be involutive, and that's equivalent to the SKT condition. So I can rephrase this condition in terms of involutivity of a subspace. It's no longer a maximal isotropic subspace, it's one that just sits inside V plus. But that's the situation we have. We have a complex structure on V plus, which is involutive with respect to the current bracket. That is an SKT structure. So it's a funny thing that the SKT structures in principle only live on V plus. They would not see the V minus, so the minus one eigenspace of the metric. There you can do whatever you like. If you wanted to have a generalized scalar, you'd have to put a completely independent structure there. If you just care about having your SKT, you could just say copy the same information on V minus, but there's no good reason why that would be of any good use. This vention here, because the Nine-house tensor was defined in terms of take the bracket of two things and see how it pairs with a third. So now I'm saying if you pick the bracket of two things in V plus, it lands back on V plus. So the way it pairs with a third, the structure is kind of contained. So if I'm here on UPQ, and I want to take the active things in V plus, where the bracket would go, this would be 1V plus 1, 0. This would be another one, lands here in this blank space, V plus 1, 0. And because by the SKT condition, the result lands already in V plus 1, 0, it will pair 0 if anything in the other spaces except for V plus 0, 1. So if I try to go again with V plus 1, 0 gets 0. If I go to this side with V minus 0, 1, I will also get 0 because the pairing between those is 0 anyway. And if I go here, I also get 0. So an SKT structure is characterized by the fact you have this top right corner here, and by conjugation, the bottom left corner here, full of zeros. So 3 of the 6 tensors that you could have vanish in an SKT structure. So that's a generalized complex characterization. To write this diagram here, I did make a choice because it started with the SKT, which was just in principle a complex structure on V plus. I do not have anything on V minus at this stage, and I can just pick any orthogonal complex structure so that I have a Hermitian structure. I can do this UPQ decomposition. But technically, for the SKT point of view, the only relevant thing, the only intrinsic thing are the diagonals. Not the UPQs themselves, but if you do the direct sum over the diagonals, that is a well-defined object for the SKT structure alone. That's a complex structure on V plus. So that's what this is saying, is that DH will have all the zeros here, so it doesn't change that far. So it picks the diagonal and only moves it either up 1, down 1, or stays in the diagonal. That's what the SKT structure does for you. So DH is very well behaved with respect to the diagonals when you have an SKT structure. If you were to do the negative one, it'll be the same thing but backwards. So you end up with like the zeros here. So negative would be if you have an integrable structure on V minus instead of V plus. Have zeros here, and then the non-trivial things are now in this other corner here. And then you see that if you look carefully, and if you have an SKT structure, which is an integrable complex structure on V plus, and you get all the zeros here, and also one that's an integrable SKT complex structure on V minus, you get all the zeros here as well, then everything becomes 0, and you get that you get just the 4 operators of a generalized scalar structure. So if you have a positive and a negative SKT structure, you can put them together to create a generalized scalar structure. So that's like a graphic proof of this result that Gualtieri proved in his thesis. But going back here, so these are the components of the intrinsic torsion. You have these 3 non-trivial components, and their complex conjugates down here. So you can focus on one of the 2 sets of tensors. I guess what I was saying is that the relevant thing is not really the components, but just what happens in the diagonal. If I add over p plus q equals to constant. So I can actually start making these operators, which are more intrinsic to the SKT structure. It's not the del plus, del minus, and this n1 and bar, but more the combination. There's the one that moves up one, which I'm going to call delta n. There's one that moves down one, that's delta bar n bar. And there's this one that goes in the diagonal, I'll call it del minus. So if you have a generalized KT, these guys are supposed to be the diagonal spaces. And I have two operators that one of them moves up in the diagonal, one of them moves down in the diagonal, and the third one preserves the diagonal. And these are natural operators you have associated to SKT structures using this generalized complex decomposition. One thing that's interesting is that if we have an actual SKT structure as we normally think of them, which is an integrable complex structure and a metric, I can just copy that integrable complex structure to the V minus. So when I do that, there's no reason why that would give me an evaluative subbundle on V minus. In principle, it doesn't. But it makes sure that J1 is integrable. So right now, I'll have this top corner here. If I do this business of just copying the structure of V minus, I have this corner here is 0 because I have SKT. And this whole row here is 0 because J1 is integrable. So I see that of all the tensors I would have if I do that business, the only one that's actually stopping me from being integrable is this one here. So a generalized scalar would be a generalized Hermitian in which all the 6 components of the Nyhaus tensor vanish. And an SKT is one in which 5 of the 6 vanish. So it's pretty close to being generalized scalar if you do the correct copying and put the correct structure on V minus. And then with that choice, you actually get the D has 6 components. One of them is going to be, that's the ones that I'm drawing here, is the delta plus, there's the N, and the delta up N is the sum of those two, because that's the one that moves up in the diagonal. The delta N bar is the one that moves down in the diagonal, and then the delta minus is just the one that preserves the diagonal here. So just try to do some Hodge theory now. So how does that help me? So first, the simplest setting of Hodge theory would be if you have just a manifold orientation and metric. Then you can form this square roots of the Laplacian. It's the case that whenever square, then we get the Laplacian, but because they have opposite signs, one of them squares to plus the Laplacian, the other one squares to minus the Laplacian, depending on the dimension you're at. They both send even to odd forms. And not only that, but they actually send either they send self-dual to anti-self-dual and vice versa, so they flip the duality of the form, or they send self-dual to self-dual and anti-self-dual to anti-self-dual, so they can preserve the duality of the form. So that means that if I was to look at the harmonics, I can decompose harmonics both into even and odd, which I already had because it's the cohomology theory here is only graded by even and odd. But I have a little bit of extra grazing because I can decompose into self-dual and anti-self-dual. So just by having a metric and orientation, I'm getting a Z2 times Z2 grazing instead of just a Z2 grazing. And that's just by looking at the harmonics and saying, are you self-dual or are you anti-self-dual? So this D plus here, for example, is the one that changes the duality. And the D minus is the one that preserves the duality. So send self-dual to self-dual and anti-self-dual to anti-self-dual. If you recall, sorry, let me go back here. Here, sorry. And now I should erase the whole thing. This one to the bin. So if you recall the way that self-dual and anti-self-dual forms work, they are compatible with this UPQ decomposition because each diagonal is made entirely of self-dual or anti-self-dual forms. So if I want to know which ones are the ones that preserve the self-duality, be precisely this bit here, the delta minus plus delta minus bar that preserves the self-duality. It sends the diagonal to itself, while the delta n plus delta n bar reverses the duality. So this one here is the D minus, I think, that I was describing later slide, and this one would be the D plus, the one that reverses the duality. So I actually can relate this specific guys with this half Laplacians, and the half Laplacians give rise to the harmonics that represent cohomology classes. So you see that you start getting the Hodge theory for Kahler manifolds appearing. So the theorem here is that if you have a compact SKT manifold, the DH cohomology actually splits into these diagonal parts. So for just orientation and metric, you have a Z2 times Z2 decomposition, and now we're actually getting this W decomposition, which is a Z grading. And this is not the grading by degree. These things in principle will be mixed degrees. So it's a completely different thing, but here is obtained by looking at the natural operators we have, which are these deltas and so on, and checking that they actually behave well with respect to the decomposition, and the Laplacians preserve the decomposition. And that's how you get this Hodge theory. The very similar way you'd get Hodge theory for a Kahler manifold. So we improved our grading from Z2 times Z2 to a Z grading. If you come from the world of my forms were like graded by degree to start with, it might not seem like a great improvement because you already had a Z grading before, but this one is more compatible with the geometry that you have at hand. And the proof is really what I just described, that you observe that the self-dual and anti-self-dual are like this. So you get the delta minus, this is like the delta bar is the diagonal that's preserved. Like this is the picture of D minus, and then D minus is the Laplacian preserves the diagonal because D minus preserves the diagonal. So you get that the space of harmonic forms decomposes along the diagonals. So the type of Hodge theorem that should be used to from complex geometry looks like this now. They have all these different Laplacians. In this case, I'm looking at delta n plus and delta n plus bar, and the Laplace is actually 1/4 of the usual Laplacian for a DH, and it's a computation to do. It's actually like it's straightforward, but I'll just leave it at that. It's actually quite pretty, but I'll leave it. I'll just like to get back to one thing before we finish, which is that if I actually had an SKT manifold and I wanted to treat it as I normally would, which is really saying I have a metric, an actual metric, I have an actual complex structure, and I would like to just use those. So I'll do this business of copying I both in the V plus, where it's an integrable involutive subbundle, and to V minus, where it doesn't have the integrability condition. Then how do I relate that back to the double cohomology, things that I would be familiar with? And that's what I was saying before. We have this bundle automorphism using the symplectic structure that relates the PQ decomposition for the complex structure with this weird one from the generalized complex one. So what you have to do is just figure out what do these different operators, the delta plus, the delta minus, the n, and so on, how do they what happens with them when I start conjugating them by this operator here. And that's something that actually can be computed. It's just a computation. And you see that the del operator, the usual del operator for the complex structure I, is related to the delta plus. And this operator here, which is just 2i del bar omega, is related to the n. So under this isomorphism, I will have that psi of del plus 2i del bar omega is going to be the same thing as delta plus bar of psi. So that's the composition. So you have a relationship between operators on both sides. And on this side here, it's an operator that's like quite standard from the Hermitian point of view. It's just the del operator and wedging with some form. So one corollary is that because I have this identity of operators, the cohomology is the same, is that if you actually were to write down this decomposition, so this is the decomposition of DH as a double differential, and it's an interesting one from the generalized complex point of view, because it's not the one you write it first, but here I'm saying that it's somehow the delta n corresponds to del plus del bar of omega. So if you write dh as del plus del bar of omega and del bar minus del of omega, then that decomposition generates at the second page. So the DH cohomology is the cohomology of del plus I del bar omega. And one thing that actually makes it nice was, let's say, even if this result, which at least is a result about usual cohomology DH, you give me the tree form, I compute the cohomology without actually having to think about generalized complex things. This one also, in principle, I can compute by hand, and I get now a statement about these things being isomorphic. In an ideal world, if you have just the complex manifold, I'd like to just say something about the Dolbeault cohomology and the RAM cohomology. And don't have these extra things hanging out, changing, screwing up. So like something that's way more topological, that would be the ideal world. And that works well when you have Hermitian symplectic structures. So let me just recall very quickly here. A Hermitian symplectic manifold is a manifold with a pair of integrable complex structure and symplectic structure. So they're both integrable, just like in the Kahler case. If you plug in the complex structure in omega here, I think here, you get something which is positive definite, but not necessarily symmetric. So that's where the failure of being Kahler is. It's just that it might not be symmetric. Currently, I think it is still a big open question for people who work on this, whether there is any Hermitian symplectic manifold which does not admit a Kahler structure. One thing that happens when you have a Hermitian symplectic structure is that you can actually pick, instead of the whole omega that was the closed symplectic form we had before, you can just focus on the 1-1 part of omega. And that is going to be an SKT structure. It's an SKT structure with the age exact. So if you do your computation, DC of omega is going to be D of essentially the 2-0 part, or the imaginary part of the 2-0 part. So we call that B for now, so you don't have to write this big expression every time. So it's a case of having an SKT structure with an exact tree form. Again, I think it's an open question in this area of research, whether there is any SKT structure with exact tree-form H, which does not come from Kahler. So they can easily produce SKTs with that, but they will be deformations of Kahler manifolds. And the question is whether you can actually get one that in a manifold that does not admit a Kahler structure. I think it's still an open question there. But I think having people who know better in the audience. So if it's not a question anymore, let me know. The result here is that if you have a compact Hermitian symplectic manifold, the Dolbeault cohomology is isomorphic to the RAM cohomology. So this is a particularly nice result, because then I got rid of all the ages and the del bar omegas and so on. It's really saying that the Dolbeault cohomology is the topological thing, which is the RAM cohomology. The isomorphism is a little bit funny. And the way to do that is that you notice that if you want to compute the cohomology of D, and you twist by dB, you just change the differential by an isomorphism, so you don't change the cohomology. So changing D with the 0 twist to D with an exact twist computes the same cohomology class. And so this is the DH cohomology of your Hermitian symplectic manifold. From the previous result on Hodge theory, the DH cohomology is isomorphic to the Dolbeault cohomology of del bar minus I del omega 1-1. And del of omega 1-1 is actually del bar of omega 2-0. So here, again, you have the case in which you have the Dolbeault cohomology twisted by an exact term. So again, twisting by an exact term does not change the cohomology. So it's the same thing as the Dolbeault cohomology of your Hermitian symplectic manifold. So it's a sequence of isomorphism that's not so obvious, but it does tell you that in a symplectic Hermitian symplectic manifold, this particular result that holds for Kahler manifolds, that the Dolbeault cohomology is isomorphic to the RAM cohomology, still holds. And with that, it's 5 o'clock, and it's the end of this Fröhliche spectral sequence also degenerated the second step. So yes, I think whenever you have this isomorphism between the Dolbeault and the RAM, because the Fröhliche spectral sequence is one that starts in page 2 with the Dolbeault cohomology, and then you continue computing cohomologies, and eventually you end up at the RAM. So every step, if you don't do anything, you just stay in the same dimension. And if anything interesting happens, you decrease the dimension. Since already in the second page, you have the same dimension as the final page must have, then you cannot do anything in any of the next steps, and the cohomology is the same. So the Dolbeault cohomology having the same dimension as the RAM cohomology is the same thing as the page, the spectral sequence degenerating on page 2. So I think it's 5 o'clock, and this is like thematically, it's a pretty reasonable place to stop instead of continuing on with deformations. So I think I'll maybe stop here and take some questions.
Okay, thank you. Thank you a lot.
Thank you for the invitation. Oh man, so many claps.
So it looked like there are no question, but I actually would be happy if there was a quick way to go through the deformation.
Sure, I think I can quickly do that. Yes.
Just get some insights.
Yeah, no, it's similar to what I was doing before. So that at least the setup is already there. So the idea is that if you look at the space of generalized complex structures, generalized scalar structures, there is some invariant there. So the parity, but if they are in the same parity, so like there's a Z2 invariant, and otherwise any two of them will be equivalent by an action of an orthogonal transformation. So it's somewhat similar to if I tell you that I have a Hermitian vector bundle, I can pick an orthonormal basis compatible with the complex structure, and they always look like Cn if they're Euclidean metric. So here it's somewhat similar, except that it's T and T star. So there's actually one further plus or minus thing going on. But if I start at one structure and want to just look at the deformations of that one structure, that discrete invariant is fixed. So any other structure that it can be deformed to will be in the orbit of the action of the spin group. So you can always do a change of basis and orthogonal change of basis to get the other one. So that's kind of the rule. If I'm doing small deformations, all of them will be in the orbit of the spin group. And then there's a question of, are SKT structures stable under deformations? So the idea here is that, let's say I have J1, I'm thinking of it as like a standard SKT structure. So J1, you can think of it as the complex structure, which I'm making it to be integrable. Can I, if I deform it, can I make so that J2 goes along and stays SKT? So it really is something thinking from the Hermitian point of view. I have an integrable complex structure, deform it a little, and I want to see if I can change the symplectic form to go with it so that it remains SKT. And then the game is similar to what I was writing before. So the deformation of J1 will be determined by something like this. So it's something wedge 2 of L bar of J1. And then we have that particular kind of combination that before it was called epsilon, now it's called alpha. And then we end up with this kind of a conjugation of the H. So instead of letting the spaces vary with my parameter, I just change the differential operator so that the differential operator is the one that actually gets the equation. And I can consider everything in terms of the decomposition of this space by the original J1, J2. And before I had this Maurer-Cartan equation appearing, and the idea is that we just have to look at the linearization, and we do a power series argument. So somehow the lack of linearity will come by picking every time a new component so that you can keep on going. So the thing you would like to consider is the commutator of dH and alpha. And then you kind of already wrote down dH has all these components. So here are the components of dH. You have del plus, del minus, del bar, etc. and n. And then I'd like to see which ones of these, like when I start doing my deformations, what happens with these components. So let's see here. So the idea is this. So if I'm just looking at J1, what do I know? I know that I'm picking an alpha, which keeps it integrable. That's the premise. I deform J1, the complex structure, as an integrable complex structure. So linearly, that would mean that I hit my canonical bundle with alpha. So I'll end up in 3 different spots. So this is like in that diamond that I was drawing before with the UPQ decomposition. I'm on this corner here, and I'm asking myself, where does my deformation parameter lands me? So end up like jump 1, and then it lands here. So my deformation parameter can have 3 components that contribute to the deformation, and they'll be here. And then the linearization is to say that if I also hit this with my differential operator D, it should be 0 in all cases. So this term here should be 0, this contribution here should be 0, this one should be 0, and this should be 0. So that's the part of the nine-house tensor being 0 that I had before. So that's this collection of zeros that I'm writing here as well. So this is an infinitesimal description of the deformations that keep J1 integrable. So this is something that I'm given, a deformation of J1 that stays integrable. And the question is, can I pair that with a deformation of J2 that stays integrable? And the idea is that if I pre-compose this deformation here, if anything that preserves the space, so first I do something, it's an overall automorphism, but preserves the J1 structure, and then do this alpha decomposition, alpha deformation, then I still have the same deformation of J1, but I have some freedom on what to do with J2. So this is what alpha will do with J2 on its own. It looks a little funny. So now I'm again in that diagram. But now I'm in here in the J2 part, and I do have an SKT structure. So that means that my differentials are one here, and I think I had one that went all the way down here. So this is where my structure already exists. So when I apply DH to things, it does all these moves for me. And then I start looking, what does alpha plus do for me? So I have alpha plus had these three components, right? I had one that goes up by two, one that goes sideways by 2, and one that goes down by 2. So now it does the same thing here. There's one that will go up by 2, or technically, because it has its complex conjugate, there will be, oh, it disappeared. So there will be one that goes down by 2, which is the complex conjugate of this one here. That would go up by 2. So there will be something here. That's what alpha is doing for you. There's one that goes sideways by 2, so that goes here. And there's one that goes down by 2, so there's one that goes here. And then I apply DH to that, and I want the result to be 0. So when I apply DH, I'll have like something that goes here, so that's the delta minus. I have the N, that is this one that goes, this one here. So it goes all the way here as well. And the idea is that I would like, so this is the diagram that you end up with. So this is the diagram you end up with. So here's the different components of alpha. They land here, here, and here. And you apply DH to that, that's the linearization. And you'd like to have this term here be 0, because that's where the component of the nine-house tensor whose vanishing gives you SKT structure lives. So you give me a parameter, a deformation parameter. I do some computations, end up with some term here. I'd like to be able to kill that term. And the ambiguity that I have is this thing that I can pre-compose my deformation with something that preserves J1. So I can pick something like of this form, which would be something that just sends it to itself. And if I look at what it does to this space, it just maps it straight down. So this one here is something that alpha gives to me once I apply DH to the deformation. And this one here is the freedom that I have to kill. And the idea is that when I apply DH, I'll get a component here. And the question is, can I use this green component to kill the red component? That becomes really the computation has to do. So you have, this is the red component. This is the green component. And you always end up with this thing. This thing here is a cohomology, is a closed element. But it might not be exact. If it's exact, then I can find a beta. If it's not exact, I cannot. So if it's exact, then I found my first beta and can kind of repeat this argument. I'm just drawing here the linearization, but you can keep on repeating this over and over. And every time you get again the question, is the class that you get here, which is always closed, is that class exact or not? And if it's exact, you pick another one here and you continue. So it's like an inductive argument similar to Kodairo's proof for I don't know if it's Kodaira or Tian Todorov, but a few proofs in complex geometry about stability of structures. One thing that would be good is if this thing here lied in a space that had the cohomology was trivial. So if you had a trivial cohomology at this level, then you'd automatically get that the problem is unobstructed, and then you'd get always can complete an SKT structure. So you can actually write down what this thing is in terms of the double cohomology, which is what you're kind of interested in. And the obstruction space is H del bar 1, 2. That's where this question keeps on happening all the time. If that class that you got in H del bar 1, 2, the double cohomology 1, 2 was trivial, then you can continue going with your argument. And if you have a non-trivial H12, then you actually can have potentially obstructive deformations. In the paper, I did write down some examples because for Lie groups, we know that if you have a biinvariant metric, it gives you an SKT structure. But once you pick a metric that, if you pick a complex structure orthogonal with respect to a biinvariant metric, it's an SKT structure. If you move it a little bit so it's not orthogonal for the biinvariant metric anymore, then in some cases you cannot make it SKT anymore. And you can even prove it because the dimension of these double things that we have that should stay constant in SKT, they start jumping up. So it becomes actually, you can prove that that's not SKT anymore. So that's the idea here. What I did was kind of give an argument which is like for the linearization. So the first step, but this is we can actually continue. So it's the at this stage, a power series argument. I fully expect one doesn't have to do the power series argument, but then I do not know if you gain any more insight by doing the functional analytic one with inverse function theorems. Does that give you an idea of what will be involved?
Thank you. Yeah, thank you. Mhm.
Can I ask you a last quick question?
Yeah.
So, I mean, as far as I know, it's kind of open to find some examples or prove that if you have SKT and you have the Hilbert lemma, then it has to be Kahler. I mean, it's kind of probably a conjecture. So I want to ask, there is some notion of the Hilbert lemma that also in this case, when the manifold is SKT or generalized scalar?
Right. Excellent question. No.
No.
That's something I was very enthusiastic about it at the time. I did have trouble with that because essentially I would like to have the bar lemma like with the double operators, and because we have this forms that are always twisting, it's always the same way that I have DH, I always have del plus something, and so I only got essentially my Laplacian identities that I would like to have for the Kähler identities. I only got them for one, as if I only had the del bar Laplacian is equal to the D Laplacian, but I do not know anything about the del. I only got half of the identities. Not only that, it's not just that part's not just a failure from me, but in fact that the operator, like the Laplacian that I should compute using del, includes del and other stuff, and then it becomes equal to the usual Laplacian. So it's not like with this framework, it will not get an identity of the del Laplacian and the D Laplacian, even in the Hermitian symplectic case.
Okay, I see. And another curiosity, generalized scalar, we don't know if they are formal or not, right?
So generalized scalar, we do not know if they are formal or not. That's correct. There is some formality result, but essentially the place where you can try to get that claim that would follow more directly from arguments that you have for Kähler manifolds is that you look at the cohomology of the Lie algebroid. So instead of looking at the double cohomology that's on space of forms, you do the Lie algebroid thing, so they're related. And the weird thing is that on the space of forms, you have the Kähler identities. On the Lie algebroid, you have a decomposition del plus del bar that satisfies like Leibniz properties. So if those two things are the same, which is when you have a generalized Calabi-Yau manifold, then you can use the Kähler identities on forms to conclude something about the del bar satisfying the Leibniz rule on the Lie algebroid and say that the Lie algebroid becomes formal. So the homology algebra of the Lie algebroid becomes formal. With that said, then it does not give you like a homotopy group. So like one of the nice things of formality for Kähler manifolds is that it gives you a topological result as well. And this, because now on the Lie algebroid world, there is no connection to topology anymore.
But do you expect them to be formal or not in the classical sense? Which is your expectation?
So I use it to think, yes, they probably would be formal. At some point when I was a PhD student, I got to look into G2 manifolds, and I thought that those would be formal as well. Like I was optimistic. I did some results on G2 manifolds that they were they tried to be formal type of thing. So if they were small topology, etc. And there are two constructions of G2 manifolds, Joyce's and Kovalev's. And then at some point, somebody, I think last couple of years, said, oh, look, here's an example of a non-formal G2 manifold.
Yeah, merchant. Yes.
Yeah, we obtained from Joyce's construction. And after that, I'm not so, like, I don't know. I really like,
Okay.
maybe Giant scalars are not formal. We don't have a lot of examples, like except for like these ones that you and Anafino have been obtaining. Lie groups, like I think that the list of non-Kähler giant scalar manifolds is kind of limited.
Okay. Yeah.
Yeah.
Yeah. Thank you very much. It was a really beautiful talk.